Murray Breeden from Shockwave Engineering. This is a technical video covering the installation and commissioning of the Shockwave Engineering Pivot Optimiser. We do have other videos which cover the functions of the Pivot Optimiser as well as other use cases of the Shockwave Engineering IoT ecosystem. The first part of the video will cover the physical installation, and then we'll go over the steps to commission the system. The physical installation includes installing the remote pressure monitoring stations at the center and end of the pivot, installation of repeaters if required, and then in the pump house, installation of the variable speed drive, the Pivot Optimiser main unit, as well as the associated sensors, including the inlet pressure sensor, outlet pressure sensor, and flow meter. We've got the radio unit inside this enclosure, an extended antenna, the pressure sensors connected into a T-piece, and we have a solar panel connected onto the top of the pipe which powers up the unit. Inside the enclosure we've got the remote unit itself as well as a battery which gets charged up by the solar panel. We have an RF cable coming in from the extended antenna, and then we've got the cable from the pressure sensor so that the unit can read the pressure values. We also have a cable coming in from the solar panel so that the unit can be powered up. This is the remote unit pivot mounting bracket. It allows the remote unit to be installed, has a mounting position for the extended antenna, and allows the bracket to be mounted onto the pivot pipe and the angle adjusted in both directions. The solar panel is secured to the pivot pipe using stainless steel cable ties. A stainless steel cable tie tensioning tool is required for this job. U-bolts are used to secure the pivot bracket onto the pivot. The size of the U-bolts must be matched to the size of the pivot pipe. This shows the completed installation of the Pivot Optimiser end unit. The end unit is usually installed on the last tower of the center pivot. If one of the intermediate towers goes to a higher point than the end tower, then the end unit can be installed on the intermediate unit. This pivot is one such case where we've installed the end unit on one of the intermediate towers. These are the components and tools required to install a remote unit on the pivot. Firstly, we have a pivot bracket and the extended antenna pole. We've already mounted the extended antenna pole onto the bracket using these U-bolts. At the end of the extended antenna pole, there are threaded inserts with M4 grub screws that are used to lock the antenna in place. We have the remote unit itself. We can open up the remote unit and see the radio unit as well as the battery pre-installed onto the backing plate. We have a solar panel mounted onto a pivot mounting plate, the external antenna, an RF cable for the external antenna, U-bolts for mounting onto the pivot pipe, and a locking ring for closing the enclosure lid onto the enclosure. Then we have the pressure sensor. What's not shown here is the fittings and the T-piece for going into the pivot itself. To mount the solar panel, we use stainless steel cable ties as well as a stainless steel cable tie tensioning tool. To mount the bracket, you need a socket spanner. You need a small socket for mounting the enclosure onto the bracket. And we need Allen keys for mounting the antenna into the extended antenna pole, and a small flat screwdriver for mounting the pressure sensor into the radio. The first step is to mount the extended antenna pole onto the bracket using the U-bolts. Then connect the RF cable onto the base of the antenna. You can screw it up nice and tight. You need to be very careful not to damage this cable and to ensure that the bend radius is not too tight. Once the RF cable is attached to the antenna, you can feed the RF cable through the antenna pole. Once the cable is all the way in, you lock the antenna in position using the grub screws. Once the cable is inserted, you secure the antenna using the grub screws. The grub screws must locate into the recesses in the antenna. The RF cable is now sticking through the bottom of the antenna pole, and you need to be extremely careful not to damage the cable. Next, we install the enclosure onto the pivot bracket. On the bottom of the enclosure there are threaded inserts, and we use M6 bolts to secure it onto the bracket. Then you can insert the RF cable through the gland, and once it's through you can connect it onto the SMA connection on the bottom of the radio. Make sure that it's nice and secure, and then we're done with the ground installation portion. The next step is to mount it onto the pivot. We've now assembled as much as we can on the ground, and the next step is to mount the bracket onto the pivot. It is possible to do the installation on your own, but it is much easier if you've got an assistant, so one person can pass the unit up to the other person who's already up on the pivot. The golden safety rule is not to go underneath anybody who's working on the pivot, and if you are up on the pivot and somebody comes below you, to stop working immediately until they've cleared the area. I'm going to move it into position. Peter, you put the U-bolt in from below. When mounting the bracket, you must ensure that the antenna is perpendicular to the ground in both directions. Next, we install the solar panel using stainless steel cable ties. To install the pressure sensor, we usually use one of the existing pivot down pipes and install a T-piece in line. Alternatively, if there's a spare port on the pivot, then the port itself can be used. Then the pressure sensor is wired into the green plug. When commissioning the unit, the solar panel should be disconnected. Connect in the green plug, which will power up the unit from the battery. When the battery is connected, you'll see the LED lights on the system come on. This indicates that the battery has got sufficient charge and is correctly connected. Once you've established that the battery is correctly connected, you can connect up the solar panel. I'm going to connect up the solar panel now. Once the solar panel is connected, then the solar LED comes on. If this LED does not come on, then the solar panel is not properly connected, or there is a disconnected wire in the system. If other remote units or the main unit in the pump house has already been installed, then this radio will start communicating with them and the RSSI light will come on. If the RSSI light does not come on, then it indicates that either the other units are not installed or powered up, or there's no radio connection. The last step is to secure the loose cables with cable ties to prevent them blowing around and being damaged in the wind. This section covers the installation of the remote unit at the pivot center. The pivot center remote unit can either be installed at the actual pivot center or at the first tower of the pivot. If you want to get feedback from the pivot, which allows a pump to be started or stopped from the pivot center, then you should install the remote unit at the pivot center. If you do not need feedback from the pivot control panel to tell the pump to run or to stop running, then you can install the remote unit at the first tower. The advantage of installing it at the first tower is that you get a better radio signal because of the higher mounting position and the possibility to use an extended antenna. The pressure sensor can be installed on an empty socket. If there isn't an empty socket, then a T-piece can be installed and the pressure sensor connected off that T-piece. We've installed the solar panel on a pivot strut, and we've made sure that the solar panel is facing north to optimize the power supply to the radio unit. We've installed the remote unit bracket onto the pivot strut. There are different options for different pivot manufacturers. Please refer to our manual for different installation options. The center unit is installed underneath the main pivot arm. This prevents us from using an extended antenna, so instead a short stubby antenna is used. To mount the antenna, our radio is mounted upside down with the antenna sticking above the metal plane of the mounting bracket. For automation mode 1 and 2 operation, the pivot optimizer receives a run signal from the pivot center panel. This run signal is transmitted through this relay, which is mounted in the remote enclosure. For remote version 2 radios, this relay intercepts the pressure signal, so when this relay is inactive, you receive a 0 milliamp signal from the pivot center. For revision 4 radios, there's a separate digital input on the radio, which receives the output of this relay directly. This cable feeds from the pivot control panel and energizes the relay to tell the system when to run the pump. The rest of the installation and setup is the same as the end unit. All pivot panels give a run output to the pump. Usually this is transmitted to the pump over a communication cable. The pivot optimizer allows this to be transmitted over the radio network. The pivot control panels have an output terminal where you can connect into the pump run command. This particular pivot panel is an Agrico pivot, so we've connected onto the WW terminal and neutral terminal. When the pivot panel wants the pump to run, these terminals are energized, and this in turn energizes the relay in the remote box. The system has now been completely wired into the pivot panel, and we can send a run command from the pivot panel to the pivot optimizer to start the pump. So we can now make sure that the pivot is in wet mode and the safety is okay, and we can press run on the system. It now sends a run command to the pump. The pump will start up, and once there's sufficient pressure, the pivot will start up and continue to run. Over here we've installed the sensors for the ultrasonic flow meter. These are the sensors over here. We've got an upstream and a downstream sensor, and they're installed in a bracket which holds the sensors in line on the pipe. These sensors have been installed on the side of the pipe so that we avoid any air that is trapped in the top of the pipe or any debris that's deposited on the bottom of the pipe. On this pipe there's a weld seam running over here, and it's important to avoid the weld seam because that will interfere with the ultrasonic signal. So we've positioned the sensors slightly below the weld seam. The most important part of the ultrasonic flow meter installation is to select a suitable section of pipe. It's important that the installation is far from any bends, T-pieces, the pump or any other flow disturbances. It is also important that a section of pipe that will not trap air is selected. In this particular section of pipe, we've got a nice straight section of pipe. It's far from any bend, far from the pump and far from any subsequent bend. The flow meter sensors should be installed at least 10 pipe diameters after any bend and 5 pipe diameters before any other bend. That means that if you've got a 200 millimeter pipe, it should be installed 10 times 200 millimeters or 2 meters after the bend. You also need to select a section of pipe that will not entrap air. So a section of pipe that goes up, goes across and comes back down is not suitable to install the sensors at the top of the inverted U because of the potential to trap air in that section of pipe. This section of pipe here is ideal because it is facing slightly uphill, so any air that does come into the system will be carried through away from the sensors. This shows the installation of the pump outlet pressure sensor. We've installed an isolation valve so you can close the valve and remove the sensor without having to drain the entire pipeline. We've also installed a small standpipe. The idea of this is that it traps a small amount of air in this section of pipe, so if you do encounter freezing conditions, you do not end up with any water inside the sensor, which then freezes and damages the sensor. Once the sensor is installed, then it's important to secure the cable to the top of the sensor or the pipe so that if this cable is bumped, it doesn't do any damage to the top of the sensor. This sensor has been installed outside the pump house in Underberg, which is a very cold location, so it is likely that the water in this section of pipe will freeze, and that's why it's important to have the standpipe in this particular location. This is the installation of an inlet pressure sensor. The farmer has welded in a 1-inch socket, and we've then installed an isolation valve so that we can remove the sensor without draining the whole line. A short standpipe to trap air in so that water doesn't go in the sensor, because if that water freezes it will damage the sensor. Then we've got the sensor itself with the connection cable which goes directly into the pivot optimizer unit. When planning the installation in the pump house, the largest item is the variable speed drive enclosure, so it's important to look for a suitable position for this first. Make sure that this can be installed and then go about installing the rest of the system. Here the pivot optimizer main unit has been installed onto the wall with normal wall mounting bolts. Once the unit is installed, then it should be powered up. If Shockwave Engineering has supplied the variable speed drive, then the power supply is included in the variable speed drive enclosure. For other VSDs, an auxiliary 24-volt DC power supply is required. At the bottom of the pivot optimizer main unit, we have a number of panel mount connectors. Firstly, we've got SMA connectors for connecting an external GSM antenna. The external GSM antenna allows us to get GSM signal to the device even in pump houses where there's very poor cell phone connection and you cannot make a phone call. Then we have a connection for the 2.4 GHz antenna. This is used for communicating between the main unit and the pivot over the local mesh network. Then we have a number of M12 connectors. These connectors are for connecting a power supply into the unit. This is where a standard 24-volt DC power supply connects in. A VSD connection. The VSD connection gives a run signal to the VSD as well as a speed signal reference. The VSD must be programmed to receive an external run command as well as an external speed reference signal. Please refer to our manual for setup parameters for different VSD models as well as a wiring diagram. Then we have a connection for the pump pressure inlet, pump pressure outlet, flow meter and pump power. The pressure inlet sensor and outlet sensor as well as flow meter are directly plugged into these units, and power for those sensors is provided from the pivot optimizer main unit with the signal from those units coming back into the unit. On the pump power, the VSD must be programmed to give its power consumption on one of the analog outputs. It should be on the 4 to 20 milliamp analog output, and then the pivot optimizer is calibrated to read that power from the VSD. If a VSD is installed that doesn't have a power measurement capability, then an auxiliary power meter can be installed. Then we have a connection for a prime relay. This allows a priming valve to be opened to prime the pump and then close the valve before starting up the pump. This timer connection allows an external timer such as a Ruoflex timer to be connected into the unit, so the system can be run according to a Ruoflex schedule. This port here is for a star delta connector. This is if you're using a suction pump which is installed in a river or in a dam and lifts water up to the main pump. This connection will allow that external pump to be started and stopped remotely from this unit. The last connection is the auxiliary port. This is used for selecting pivot A, B or C in the case of operating in mode 0 or mode 1. On the front of the unit we've got a run switch which can either be in the off, run or remote run position. If it is switched into the run position, then it will run the pump directly. If it is in the remote run position, then it will look for a run command from the timer connection, and that is where the Ruoflex timer will allow operation of the system. On the front of the unit we've got a 2-line screen so that you can see the current status of the system. Within the system we've got a series of menus. So we've got main menus and sub menus. You can navigate through the main menus using the main menu buttons, and within each sub menu you can navigate using the sub menu buttons. When the unit is powered up, it displays the firmware revision. In this case it is firmware revision 2.21 that is loaded onto the system. You can then navigate through the menus, starting with the quick menu, and you can go down to analog to see all the analog inputs, digital to see the digital inputs, control to see the control parameters that have been programmed into the unit, including the set points, communications to see the addresses of the radios as well as the cell phone signal that is being received by the unit. Power supply shows the voltages of the power supply on the main unit as well as the remote and the repeater unit. PID controls shows the detailed PID setup of the system. Most of the parameters that you need to see have been arranged under the quick menu. So we can go through the quick menu and review all the sub-menu items. Firstly, we've got the pump pressure inlet, pump pressure outlet. It's displaying the values as well as the units. You'll see that the unit of pressure inlet is kPa 1. We just use the kPa 1 to indicate when we're getting new settings through to the system and to ensure that the system has received new settings. So when we adjust the settings, the next time we'll make it kPa 2, then you can check on the screen that you have kPa 2, and then you know that you've got the other settings. The next items on the menu are flow rate and power. Then we've got pivot A pressure at the center and pressure at the end, and the value in kPa. You'll see that the pressure at the center is sitting at -359. That is because that sensor is disconnected, and when we go through the installation of the pivot center pressure sensor, we'll explain why that sensor has been disconnected. We then have pivot B, pressure at center and end, if pivot B has been installed. In this particular installation there is no pivot B, so there is no signal coming from pivot B, and when we have no signal we display a value of -75. -75 is a special value to indicate no radio signal. Then we have pivot C, pressure at the center and end. Again, there is no pivot C on this system, so the value is displayed as -75. Pump speed, we're not running the pump at the moment, so the command speed to the VSD is 0 Hz, and we're sitting at pump status 3, which is a remote shutdown, which means that it is being shut down from the pivot. In the manual, we describe the other status numbers and their meanings. Then we've got local run on and run command off. Local run is the position of the switch, and run command is what the pivot optimizer is telling the VSD to do. In this case, we've got local run on, but the run command is off because the system has been remote shut down from the pivot. We can see if we turn this switch to off, the local run will go to off, and then we can put it back to on, and you'll see it will say on, but the run command stays off because the system has been remotely shut down from the pivot. The next menu item is pivot A is on, pivot B is off. This pivot A on means that when the system is running, it will control the pivot A pressures. It will not control any pressures on pivot B at the moment. It's essential that the system is trying to control the pivot that is on at any particular point in time. If on the system it displays pivot being on, but no water is going to that pivot, it will attempt to get that pivot up to pressure, but obviously water cannot get there, so the system will end up ramping up to full speed. The next menu item is the pump efficiency. At the moment the pump is not running, so it's giving us a negative, very low value. When the pump is running and there's an inlet pressure sensor, outlet pressure sensor, flow meter and power meter connected to the system, it will indicate what the combined pump and motor efficiency is. The first step in commissioning the unit is to ensure that the system is receiving GSM signal from the cell phone network. The system receives settings from the web server and transmits values back to the web server, so it is critical that a cell phone connection is established. The strength of the cell phone connection can be seen under the Communications menu under GSM SS. That value is displayed as a percentage, and the value should be higher than 65 to ensure reliable communications. If the value is lower than 65, then a more powerful antenna or a directional antenna should be installed. The next step of the commissioning process is to ensure that there is radio signal from the pivot and the repeater units through to the main unit. We do have utility software that can be run on a laptop that can do a detailed site survey of the radio signal between all the units. On the pivot optimizer itself, you can check if you're getting signal or not by going through to the power supply main menu, and under power supply you can go through each unit. Firstly, we've got the master, which we're not interested in right now. Then we can go to pivot A, center, battery and panel voltage. Here we can see that we've got 14 volts on the battery, 19 volts on the panel. If it's during daytime, we need to ensure that we do have panel voltage. If you're receiving 0 panel volts and it is during the day, it means that the solar panel has not been connected properly. When the solar panel is charging the battery, you'll see a battery volt of around 14 volts. At night, this voltage will drop to approximately 12.6 volts. When the voltage drops below 11.3 volts, the repeater units will stop transmitting. On the next menu, we can see pivot A, end, battery and panel voltages, same procedure there. Then we can go through to pivot B, center, battery and panel voltages. Now you'll see these voltages are displayed as -1. That is because there is no pivot B on the system, so the system is not receiving a signal, and in the case of voltages it displays a -1 if there is no signal being received. We can carry through to pivot B end, pivot C center, pivot C end, and then we can look at repeater 1, battery and panel voltages. No radio has been defined on this system, so it is still being displayed as 0 volts, and the system can also display the battery and panel voltages of repeater 2. We've never had to use a second repeater, usually one repeater suffices. Once the GSM signal and site radio signal have been checked, the next step is to set up all of the sensors that connect into the unit. We can start with the pressure inlet and pressure outlet sensors. Under the quick menu, you can see the pressure inlet and pressure outlet values. In this case, the sensors have already been connected to the pipeline, and it's important to check that these values are reasonable and make sense. In this particular pump house, the pump house is below the dam wall, so we have a flooded suction from the dam, and we're getting a reading of 46 kPa on the inlet pressure sensor. 46 kPa corresponds to a 4.5 meter water head, so what you can do is verify that you've got approximately 4.5 meters of water in the dam. So it's important just to check that the values here correspond physically with what's going on in your pumping system. The pressure outlet value that we've got is 196 kPa. In this case, the outlet pressure sensor has been installed after the non-return valve, so it is picking up the static head between the pump and the pivot center. In this case, 196 kPa corresponds to about 20 meters of static head between the pump and pivot, which corresponds to the physical installation. The Pivot Optimizer gets its calibration settings from the website, and each particular pressure sensor has got its own calibration range, which must be entered into the website. We typically use -1 to 9 bar sensors on the pump inlet so that we can capture situations where there's a vacuum pressure being generated on the pump inlet, and then 0 to 16 bar sensors on the pump outlet. Now we can check that the right sensor values have been entered into the website by disconnecting these sensors over here. Now I connect up my inlet pressure sensor to the system and connect the cable into the corresponding port, and you'll see that the value that we're receiving for pressure sensor that is not connected to the pipeline is -1 or close enough to 0 kPa. If you receive a value anything other than 0 or maybe from -1 to +1 kPa, it indicates that the calibration range entered into the unit is incorrect. I can then connect up an outlet pressure sensor into the system. You'll now see on the unit our outlet pressure sensor value is sitting at -3, and the sensor is not connected to a pipeline, so we've got a value that's between -5 and +5, so that indicates that the calibration range for this sensor is correctly entered into the unit. The sensors that we use in the system are 4 to 20 milliamp sensors. That means that when the sensor is at the lower end of its operating range, it will give a 4 milliamp output. So for example, if it is a 0 to 16 bar sensor, when it is giving 4 milliamps out, it corresponds to 0 kPa. When it is giving 20 milliamps, it corresponds to 1600 kPa. In this case, we have disconnected both the inlet and outlet pressure sensors from the system, so the system is measuring a value of 0 milliamps. It is now displaying the 0 milliamp value, which in the case of the inlet is -349, which is close enough to -350. In the outlet pressure sensor, it's -399, which is close enough to -400 kPa. In our manual, we've got a table of the different calibration ranges, and in that table, you'll see that a 0 milliamp value of -350 corresponds to a -1 to 9 bar pressure sensor, and -400 corresponds to a 0 to 16 bar pressure sensor. Now I'm going to illustrate what happens when you connect the incorrect sensor up to a particular port. In this case, I've got a 0 to 16 bar outlet pressure sensor, and I'm going to connect it to the inlet pressure port, which has been calibrated for -1 to 9 bar sensor. When we plug it in, it takes a couple of seconds for the value to stabilize, and you'll see that the value has now stabilized at -102 kPa, even although the sensor is sitting at atmospheric conditions. So it should be giving a reading of 0 kPa, but it's giving minus 100 kPa, so that value is obviously wrong, and it is physically not possible to have a reading of minus 102 kPa. So when you get a reading like that, you know that there's something wrong with either the calibration range or the sensor that has been installed. Now I have an inlet pressure sensor, which is a -1 to 9 bar unit, and I'm going to incorrectly install it on the pressure outlet port. Now you'll see a pressure sensor that is sitting at atmospheric conditions, which should be giving an output of 0 kPa, is sitting at a value of 158 kPa. So again, obviously there's something wrong with this installation or calibration. We're going to go over the setup of the flow meter control unit. The first step is to select a suitable location to install the sensors. Then the circumference of the pipe is measured, as well as the wall thickness of the pipe. The wall thickness should be measured with an ultrasonic thickness gauge. Once we've got the parameters of the pipe, we can start entering the pipe parameters into the flow meter unit. We start by going to menu 10. We press menu, up arrow, across we've got to menu 10, press enter. This asks for the pipe outer perimeter. We've already set this up as 692 millimeters. We can enter that again by going enter, up arrow till we get to 6, across, up to 9, across, up to 2, enter, and we've got our pipe outer perimeter entered. The system works out the pipe outer diameter from the perimeter. It's usually easier to measure the perimeter than the diameter. If you have got a very small pipe, then you can enter the diameter directly. Then we go across to the pipe wall thickness. We've used our ultrasonic thickness gauge to determine that the wall thickness was 4.6 millimeters. When you're using an ultrasonic gauge, you should also judge the result to see if it's reasonable. Most steel piping that is used around a pump house is between 4 and 6 millimeters thick. Parrot pipe used on pump inlets is around 1.2 to 1.8 millimeters thick, and PVC piping can vary from around 3 millimeters up to about 9 millimeters thick. The system then calculates the pipe inner diameter based on the outer diameter or perimeter and wall thickness, so you don't need to enter anything here. Then we enter the material of the pipe. If you've got PVC, you can press enter and scroll through till you get to PVC, press enter to take the reading. We're going to take it back to carbon steel, press enter, go through to the next menu item. This pipeline does not have any liner. If we do have a rubber lined pipe, we can enter those parameters into here. We need to select the fluid type. In this case it's water, but other common liquids can also be entered into the system. Then we tell it what transducer type we've got. Our standard transducers that we use with the Pivot Optimizer are clamp-on M2 sensors, so ensure that those sensors are selected. We can select different mounting configurations. In this case we've got a V mounting, which means that the ultrasound signal will take 2 passes through the pipe in a V pattern. We can also select W, which will result in 4 passes of the ultrasound signal, N, which would be 3 passes, and Z, which would be 1 pass. We'll put it back to V, enter. The system then tells us the transducer spacing. Now it's told us that the transducers should be 186 millimeters apart in this particular case. For different pipe materials, different pipe diameters, wall thicknesses and fluid types, it will give you different transducer spacing. So you have to enter the pipe parameters first, as well as the fluid setup, before the system will then tell you your transducer spacing. Once you've got the transducer spacing from the system, you go and install the transducers at that spacing and then carry on entering the rest of the parameters into the system. The next step of the setup is to set up the analog output parameters. This is so that the pivot optimizer can read the flow rate from the flow meter. The analog output setup starts at menu number 55, so we can go menu, up arrow till we have 5, cross, up arrow till we have 55, press enter, and now we start off with the mode selection. In this case, it's already been set to a 4 to 20 milliamp output. We can select other outputs on other parameters. So in this case, it wants to output energy, velocity. We can have a 20 to 0 to 20 if we're having negative flow in the pipeline, 0 to 4 to 20. And we can have a 0 to 20 milliamp analog output, but we want to stick to our 4 to 20 milliamp analog output. So we accept that setting, go on to menu 56, which is the output value at 4 milliamps. You want to set that to 0 cubes per hour. The next menu is menu number 57. This is the output that corresponds to 20 milliamps. Now in this particular pivot, this pivot runs at approximately 100 cubes an hour. So we've selected a maximum analog output of 200 cubes an hour. So we will use 50% of our total available range. The flow meter does do its own internal diagnostics to ensure that it is getting a valid ultrasound reading through the pipe. We can check the diagnostics by going on to menu 90. We go menu, up arrow till we get to 9, cross arrow, now we've got 90, press enter. Now we're on menu 90 and it's telling us that our upstream signal strength is 77, downstream is also 77, and quality is 96. These up and downstream values should be greater than 75 and the quality value should be greater than 80. We can then go right arrow and we can see Tom divided by TOS times 100. Now that is a percentage value reading which calculates the expected sound speed versus the actual sound speed and expresses it as a percentage. Allowable values range between 97% and 103%. If the value is less than 97 or greater than 103, then it indicates that the flow meter has been set up incorrectly or the sensors are in the incorrect position. The flow meter has been set up to output from 4 to 20 milliamps, and in this case it's been set up to give 0 cubes at 4 milliamps and 200 cubes an hour at 20 milliamps. The pivot optimizer is calibrated from 0 to 20 milliamps. That means that you have to work out what the equivalent 0 milliamp value would be. In our manual, we do have a table of normal calibration ranges on the flow meter with the corresponding 0 milliamp value. At the moment, the flow meter is giving an output of 0 milliamps and the pivot optimizer has been calibrated from minus 50 cubes an hour at 0 milliamps to 200 cubes an hour at 20 milliamps. So when we're giving an output of 0 milliamps on the flow meter, it's giving us minus 50 on the pivot optimizer. We can then go to 4 milliamps on the flow meter and you'll see that the pivot optimizer is changing to 0 cubes an hour. We can then go to halfway through our span. So for a 4 to 20 milliamp output, halfway through our span is 12 milliamps. So we'll go to 12 milliamps. And remember that this flow meter has been set up to give 0 to 200 cubes an hour. So on 12 milliamps, it will correspond to an output of 100 cubes an hour. We can then look on the pivot optimizer and we've got 100 cubes an hour. We can then go up to our full span, which is 20 milliamps. Now that corresponds to 200 cubes an hour, and we can check on the pivot optimizer that we're getting 200 cubes an hour. We are getting it. So now we've set up the flow meter and we've checked that the flow meter output corresponds to the flow on the pivot optimizer. When any settings have been changed on the flow meter, the setting changes must be saved into the unit's memory, otherwise when the power fails, those changes will be lost. We save the changes by going to menu 26. When you go into menu 26, you press enter. When you've pressed enter, you get a right hand arrow to say that it's now ready to solidify the settings. You press enter again, the unit beeps, goes through a diagnostic process, and then goes back to menu 0. You must ensure that the unit has gone back to menu 0, and then you know that it has saved its parameters into memory. The Pivot Optimizer will work with any brand of VSD. The VSD must be set up according to the parameters of the motor so that the VSD will trip if the motor exceeds its allowable ranges. The VSD must then be set up to receive an external run command from the Pivot Optimizer as well as an external speed command from the Pivot Optimizer. The VSD must then be programmed to give an analog output corresponding to the power consumption of the VSD. That analog output should be a 4 to 20 milliamp analog output. Some VSDs allow the range of the 4 to 20 milliamp analog output to be set, while other VSDs have got a fixed range of 0 to 2 times the nominal power of the VSD. Whatever the analog output range of the VSD is, that corresponding range must be entered into the Pivot Optimizer. We do have a table in the manual which gives the standard ranges on the Pivot Optimizer as well as a standard wiring diagram. Please refer to the manual for further details as well as setup parameters for some models of VSDs. The Pivot Optimizer has got 3 automation modes. In mode 0, the Pivot Optimizer only looks at the local run command and it doesn't have any run feedback from the pivot. In mode 1 and mode 2, the Pivot Optimizer needs the local run command to be on and it needs to receive a run command from the pivot itself. In mode 1 and mode 2, if the pivot gets stuck, then the pivot will send a stop command to the Pivot Optimizer so the Pivot Optimizer can stop the pump and you don't have any overwatering. In mode 1, the pivot selection is done locally using a local switch to select either pivot A, B or C. In mode 2, the pivot selection is done from the pivot itself. This Pivot Optimizer has only got one pivot operating on it and it has currently been set in mode 0, so it is ignoring any run command from the pivot. So we can start the system directly from the run command on the unit. You'll hear the VSD starting up and then the motor starting up in the background. When it's starting up, we can monitor the startup parameters from the quick menu. Firstly, you can see that the pump outlet pressure is going to start increasing from 200 kPa to a higher value. Now the outlet pressure is increasing, so we're getting 240 kPa. The flow rate is starting to increase and the power is increasing. At the pivot itself, we've got 32 kPa at the center and 3 kPa at the end. Effectively, we've got no pressure at the end, and that 34 kPa just corresponds to the static head in the pivot itself. Now flow rate has increased to 60 cubes an hour, power has gone up to 6 kilowatts. During startup, the flow rate should not exceed the allowable flow rate capability of the pump, otherwise damage to the pump will occur. This is typically 10% higher than the best efficiency point of the pump. In this case, the pump best efficiency point is 100 cubes an hour, so that flow rate should not exceed 110 cubes per hour. The power should not exceed the maximum capability of the motor. In this case we have a 22 kilowatt motor. That refers to 22 kilowatts of shaft power. The electrical power, which is being monitored here, is approximately 10% higher than the shaft power. So this power should not exceed 25 kilowatts. The outlet pressure is increased slightly and the inlet pressure has decreased slightly because there's a slight restriction on the inlet pipework. Our flow rate has now increased to 90 cubes an hour and our power is sitting at 9 kilowatts. We haven't increased the pivot center or end pressure yet, so the water has not reached the pivot yet. We can see the command speed that is being sent to the VSD. We're telling the VSD to run at 35 Hertz, so we can look on the VSD and check that the VSD is running at 35 or now 36 Hertz. The flow rate has now increased to 100 cubes an hour with the power sitting just below 12 kilowatts. Now we're starting to see the center and end pressure both increasing. So it means that we do have pressure at the pivot center. We're getting 55 kPa at the pivot center with 9 kPa at the pivot end. The flow rate has increased to 105 cubes an hour with the power sitting at 13 kilowatts. This is well within the limitation of 110 cubes an hour and 25 kilowatts. The center pressure is almost at the control set point with the end pressure at 60 kPa, so it's about half of the required pressure. The pump outlet pressure is now increased to just a bit above 300 kPa, so we're starting to get an increase in pump outlet pressure. The flow rate is sitting at 107 cubes an hour, still within our limit of 110, and our power is sitting at 15 kilowatts. The pivot pressures are still increasing. The set point is 120 kPa for both the center and end, so we still need those pressures to rise a bit more. Our pivot center and end pressure are now both above 120 kPa, so they are higher than the set point. We will get a small overshoot in pressure. We see that we're sitting at 130 kPa on the pivot end. The pivot optimizer will now slow the VSD down so that the end is sitting at 120 kPa and the center will be sitting at a higher pressure. The pivot optimizer is now bringing the VSD speed down and we're sitting very close to the set point of 120 kPa. The pressures have now stabilized and we've reached our normal operating condition. The system is controlling the pivot A end pressure to 120 kPa. To achieve an end pressure of 120 kPa, the center pressure is sitting at 150 kPa. This corresponds to the pivot facing slightly uphill. If the pivot was facing downhill, we would have a slightly higher pressure at the end and we would have 120 kPa at the center. During startup, initially there was no pressure in the system. Then as the speed of the VSD increased and water got to the pivot, we had a small overshoot in pressure, reaching a maximum overshoot on the end of 140 kPa, and now the system has stabilized to the normal control pressures. We can now review our other operating parameters. The flow has come down to 96 cubes per hour, which corresponds to the flow rate package of the pivot, and the power sitting at 13 kilowatts. Our inlet pressure is sitting just below 40 kPa. This is a small reduction from the 45 kPa we had before the pump started, and that corresponds to the pipe friction in the pump inlet. The outlet pressure is sitting at 350 kPa, which is a nice low pressure and is the required pressure to achieve the pivot center and end pressures. We can now shut down the system by turning the local run command to off. A major cause of pump damage is blocked inlets. We built a protection system into the pivot optimizer to shut the pump down if the inlet gets blocked. At the moment the system is running stably, and on the screen we can see that the pump inlet pressure is sitting at 35 kPa, which is well within the operating requirements of the pump. We can simulate a blocked inlet on the system by starting to close off the inlet valve. As I close off the inlet valve, you'll start to see that the inlet pressure reduces until ultimately the system trips. So we'll start off by closing the valve by a small amount. The inlet pressure has now dropped from 35 kPa to 32 kPa, so closing the valve has had a small impact at this point. We'll continue closing the valve and monitoring the pressure. I've closed the valve some more, and now the inlet pressure has dropped right down to 10 kPa. I've closed the valve even more. The inlet pressure dropped. The last value that we could read was minus 14 kPa. It then dropped down to the inlet trip point of minus 20 kPa, and the system has tripped. You can see on the screen it says error trip on inlet pressure. So it displays to the operator that the system has tripped, why it's tripped, and then it displays on the website that we've got a trip on inlet pressure. It now forces the operator to come to the pump house and inspect why the inlet has got blocked, and then unblock the inlet before restarting the pump. To restart the pump, the operator must cycle the switch to off to clear the trip condition, and then put the switch back on again to get the pump to restart. You can now hear the pump starting up again, and now I need to open up the valve so that it won't discover a blocked inlet. Different trip set points can be set according to each particular pump model. The system can also send an SMS alert if the inlet pressure drops too low, so that you can get pre-warning if the inlet is starting to block and avoid a situation where the pump trips. If the inlet pressure sensor fails, then the sensor can be unplugged. The pivot optimizer detects that there is no pressure sensor, and then it ignores the inlet trip condition. The final commissioning step is to check that the pivot optimizer is transmitting the values that it is monitoring through to the web server. So I can look through on the web server now and see that the values that are coming through are valid, and I can check the timestamp of the values that have come through.